In the morning we did the monatomic gases, and I will come back. There is one part we did not do, which is a lot of fun. We will come back to that, but I just want to start fresh with the diatomic gases, which has a huge number of very important results that we use in everyday in statistical mechanics in liquids and gases and solids. And you will see that monatomic gas results are used also in the diatomic gases. That is one of the reason I want to straight go there and get those things done to get started. Okay. So, there are diatomic gases of these additional degrees of freedom, not just translation. We have rotation and vibrational degrees of freedom. Important difference now is that while translational degrees of freedom by and large except at very low temperature can be treated classically, vibration cannot be treated classically, vibrational degrees of freedom, except some cases, and we will discuss like normal modes of very soft modes and low frequency modes. The vibration that we see in molecules, that cannot be treated classically. Rotation is on the border line, and you are better off doing it quantum mechanically, and they are the most realistic things, because as we say our diatomic gases are essentially noble gases, but most of the other molecules that we nitrogen, oxygen and all these things are diatomic. So, this discussion today we will do will be extended to polyatomic molecules like water and ammonia. We will discuss a lot of things on water and ammonia, which will be very important. And then applications, we will do specific of solid, entropies. Okay, these are applications, we will not do too much of that, but we will mention them how these things go in. It is the equations we will derive today are used in understanding gases, understanding proteins and DNA. It are very well known examples, and these are what are the true many body systems, which we usually in our chemistry vocabulary, which is so much saddled with individual atoms and molecules and quantum chemical calculation of them, we hardly do many body phenomena. But when you do many body phenomena where many particles are interacting with each other to give such phenomenon as phase transition, we need to do these interacting many body systems. However, before we do the interacting many body systems, we need to understand non-interacting many body systems. In the morning we did monatomic gases, and now we are going to diatomic gases, and diatomic gases introduced many profoundly important concepts, which will again will be used in many cases, many applications, and these are just some of them which we will now go to. Okay. As I said, it is very important. After preliminary things will get more mathematical, but nothing very difficult. So, remember that if you have such a diatomic molecule, then degrees of freedom, there is a 3 translational degrees of freedom, we model by the center of mass, then 2 rotational degrees of freedom and 1 vibrational degree, total is 6, 2n. So, then when you have a high temperature, when the molecule rotating very fast, there is a coupling between rotation and vibration that comes in. What is the name of that coupling? You have done that in your undergraduate. Remember the QR branch of spectroscopy, huge amount of things done by Moore and Castellan. You know, have some interest, for God's sake. These are very nice important things, because they give huge amount of molecular information. Okay, that because these are called Coriolis coupling, and also some other forms of coupling that comes when for example, a molecule rotates very fast, then the bond, another is centrifugal. So, there are 2 things that come in. When rotate very fast, then the bond can get stretched, and that those are the called anharmonic effects. But at low temperature, we can low temperature these things can be ignored. So, we can approximate low temperature by rigid rotator. which is much of the time okay in low temperature. By the 300 Kelvin room temperature, you are a little bit on the borderline, you know. We start seeing signatures like in QR branch of where one sees in vibrational spectra the rotational level dependence, and that has been enormously important study in 1980s, that to see the rotational level dependence of vibrational or electronic luxation. That was a big thing in those days, it was considered to be. So, remember the Nobel Prize that Ahmed got in 1998, there is a experimental results were done in 1987, used many of these things to establish certain reaction pathway. Okay. So, if we now assume that these things are independent of each other, rotation, vibration, electronic independent of each other, that is an approximation. Yes. Rotation, there is a very good question that can also come, but that can come by the way, for example, if you have a large scale collision, then you can have a coupling between rotation and translation, but in usually that is weaker than in the rotation, vibration, rotation coupling. Okay. Now, so if they are non-interacting and they are independent, then total molecular partition function, Qm starts for molecule. Molecular partition function is a product of the individual partition functions. That because if they are independent, the energy levels of each are different, and partition function is sum of the energy levels. You understand that? Okay. Q is sum over e to the power minus ei by kBt, and this part I think I will probably remind you few times, because this we have not done properly or in great detail. So, partition function, if I say Q notation, then e to the power minus ei by kBt, Boltzmann constant. Now, sum over I. Now, since if ei depends on ei electronic plus ei vibration plus ei rotation plus ei translation, then you go some, then you separate them out, because this goes in the exponent, this all becomes product. So, this is then a non-interacting molecular partition function. Now, the important thing is that electronic energy levels. Now, I have asked you a question that what is the typical electronic energy levels in atoms, in molecules, and how does it compare with the vibration, rotation and translation. Let us start with translation. What is the energy gap between two? If I do quantum mechanics, then I get that particle in a box. Give me a number. What is the typical number of energy level spacing between two translational energy levels? This kind of tells you whether you think at all or not. So, you have done all of these things. You are doing statistical mechanics, and you should be able to tell what is the energy level, what is gap in translation. Say loudly. And so many of you should make at least one guess. It is okay to be wrong, but you should have some guess. Still okay, I give you one number. Room temperature 1 kBt is 206 centimeter inverse. Then how many centimeter inverse? That is what experimentalists do, and I worked a lot with experimentalists. How much? Okay, 10 centimeter inverse, that is a good guess. How much is rotation? How much more? That is actually correct. No, much more than about say 100 or maybe 50 centimeter above, depending on the moment of inertia. Now, vibration, what is the energy levels in vibration, molecular vibration? This you guys should do, because this we did a lot in undergraduate. What is the vibration gap between vibration energy levels, say for nitrogen or oxygen? Exactly 3600 centimeter inverse. One is symmetric stretching is 36, I think 60, and asymmetric stretching is 3700 centimeter inverse. How much is bending? OH bending? Huh? You said something correct. Next one. It's very important, the OH bending. That plays a very important role in your body. So, I'll ask you. So, I'll continue. I'll come back to it. So, translation is much less than kVt. So, at normal temperature, translation is like a continuum. Rotation is kind of borderline. Low temperature, it also discrete, but high temperature is continuum. Vibration, if it is asymmetric stretching is 37, bending is 1885, then that is about 10. Bending is 10, but others are typically 15 to 20 times. So, that is absolutely quantum. How much is electronic energy levels? See, you cannot you will not be able to talk with an experimentalist if you don't know these basic things. That is what they are doing all the time in IR, FTIR, NMR, these are all the things. How much is electronic energy levels? More than 10 centimeter, 10,000 centimeter inverse. So, 10,000 centimeter inverse means you have something 50 kVt or so. So, gap between ground state and excited state is that huge amount. So, that is why it does not affect, there is no population at normal temperature in the excited electronic state. Everything happening in the ground state. Then we do not need to carry this around. This is also the reason when the solid state physicist, let us not talk about solid state chemists, I do not know how much they really follow things. Solid state physicists never bother about temperature. They do not need to do statistical mechanics for much of the time. The reason because that when they talk, they are talking of the electronic excitation much of the time. So, they are talking of this huge energy gap. Okay. Let us now do vibration. So, we have to do it quantum, then we have done translation. Translational part remains the same as we did in the morning. Then we do vibration, then we do rotation. Okay. So, this is a half nu square x minus x square. So, this is m L square and this frequency 1 over t square. So, this is energy ml square by t square. It is reduced mass of the system. In this case says that I am going to 1 degree reduction of degree of freedom. That means my A is, this is my reaction, my coordinate. Now, we have to solve this. Now, tell me how we will go about it now. Here I say 3000 centimeter inverse, 15 kVt, all the numbers are there. Now, tell me one thing, how do I go about it now? Okay. The way I go about it is I solve the quantum problem, Schrodinger equation, and this is the energy levels. This part all of you have done many times. Okay. And then vibrational partition function, this just sum over these things. With sum n from 0, that is a big difference, 0 to infinity. Okay. If n equal to 0 to infinity, then this quantity half h nu by kBt, there certainly here and there are some mistakes, we have to find the mistakes. I asked my student to this, there is a 2 missing here. Why they went to write these things, I do not know, he should have just say that. Okay. There should be n plus half h nu, so e to the power minus half h nu by kBt would come out. Remember this slide we need to change. Okay. And then this goes out and then we sum n equal to 0 to infinity e to the power minus n h nu by kBt. Now, this sum can be done, and tell me what is this sum? This is the energy level, so I have to divide kBt like ei by kBt, this is the thing that is here. So, e to the power minus kBt does not have any n, it comes out, that comes out here, actually that should come in front actually, okay, but we can live with that because that has no n. Then I have brought it here, then I have to sum n equal to 0 to infinity minus h nu by kBt. So this now n equal to 0, so n equal to 0 is 1, then this now e to the power minus h nu is the x, okay. So it is 1 plus x square plus x cube, that is the geometric progression, and then that is equal to 1 over 1 minus x, and x is e to the power minus h2 by kBt, so it is 1 minus h2 cube, and this quantity comes here. So we have but this is a very beautiful result, really nice result. The vibrational partition function e to the power minus h2 by 2 kBt 1 minus, very pretty, okay. And this is the one we will discuss more about it, okay. Good that we corrected it. So again the full glory the equation. Now this defines temperature, which is also the one actually done by Debye. So now h nu by 2 kBt, this kind of game I divide by a theta vibration. So I see this quantity h nu by kb has the dimension of temperature, because exponential has to be dimensionless. So I define as the vibrational temperature, and vibrational temperature, as I said, would be 10, 15 or 20 times the normal temperature, okay. So it's theta vibration by 2t 1 minus e to the minus theta vibration by t, okay. Now from this now we are going to go, this is the form we use, this is the form what I used by Debye when I was doing the specific of it, we might come back to that. Now so free energy I know, this is a canonical partition function free energy. Now let us again slightly go back, let me repeat how we did this calculation. We are going to calculate the canonical partition function. We have a system that characterized by NVT, and then the quantum mechanics giving us the energy levels. In classical system, quantum mechanics gives up the force field, that what you guys use, that the particle interact with Lennard-Jones. Lennard-Jones parameters were initially obtained from experiments. By fitting, they found the small a and small b of van der Waals parameters and the Lennard-Jones. Lennard-Jones actually found it, what bears his name. So either experiment or quantum calculations give me the potential force field. Here quantum calculation will give me these quantities, and this mass we know, but these are the quantum values. Once quantum gives us that, with the assumption of we get the energy levels. Once we get the energy levels, we are now going to get the vibrational partition function, and here the temperature T is there, okay. Now and then this follows. So now this canonical partition function has the temperature in it. We are now going to calculate the free energy. So NVT, now the vibration, this is a single one vibration, but if there are n number of vibration, then what will happen? We have discussed it many times, you should be able to tell me. If I have n number of non-interacting harmonic oscillators, exactly will be the same, and they will be to the power n, right. So capital Q vibration NVT is Q vibration okay. So if that is the case, then ln Q, that Qn comes in front, n kBt, ln this quantity. Now a minus sign is there, minus sign is here. So now these are two logarithmic terms, I take that. So in the first term, this one I get n by 2 h nu, kBt cancels. Second one, n kBt remains, since in the denominator minus and minus gets cancelled, then I get 1 minus e to the h nu. So this is the canonical partition function of n number of harmonic oscillators. Now I get to go to entropy, S minus dA dt, and S then minus, from there I take the derivative dA dt. This guy has no temperature dependence, And by the way, where this term coming from? Please tell that. Where is this term coming from? It is very, very important where this term coming from. It is 0. No, it is 0 vibrational level. The famous 0th vibration energy, which saves the uncertain principle. So, even at 0 Kelvin, this motion remains. This is amazingly important thing. So, it is the 0 vibration energy level. Okay, that is this term. That is no temperature dependent. So, that term drops out, and so now let us do this. This I have to do temperature derivative. One is just nkBl in this term. Next term nkBT, then just like we did in translational case, we take, then that comes as 1 over minus this thing. Then I go inside and take derivative of that, and that then give me 1. I recover again e to the minus h nu by kBT. Minus is here plus another minus from 1 over t derivative. So, that minus 1 over t square. Okay. And now I take that t out here, and there was a t in front here. So, that t and t square here gives me this t here, h nu by t, because that comes from derivative, and then this is the quantity, because I said derivative will bring that here, and 3 negative makes it negative, that negative comes here. Okay. So, this, then when you do this derivative, come here, you do again the derivative, you say this is just nkBl in this term, and then derivative this term comes in denominator. So, then this term plus this term. Okay. So, this is the expression of entropy. So, one important, very important thing is that there is a very strong dependence on the frequency of the harmonic oscillator, because it is in exponent everywhere. Entropy is strongly dependent on the vibrational frequency, which is a very important thing, because since nu is large in atomic and molecular cases, this does not contribute much to thermodynamics. So, many times in our calculations we do not take vibration into account. When you are doing simulation of water, you do so SPCE or T4P, but you do not have vibration there, or any other systems, we just do not, that because this is the reason. However, when you have big proteins, there are many vibrational modes which are low frequency, which are conformational vibrations. DNA, enzymes, proteins, or even when you are looking at low temperature glasses, there are these. So, at low temperature for solids, this becomes classical approximation, of course not valid, but quantum nature of vibration leads to decrease in the specific heat. This is the famous, remember, lowering of specific heat to the temperature. What is the asymptotic, what is the Dulong-Petit's law? Dulong-Petit's law tells the specific heat of a solid is equal to 3R, very, very good, 3R. 3 by 2 comes from A, and translation 3 by 2 by vibration. Okay, we will derive that in a minute. But what Einstein tried to explain, that high temperature it goes to Dulong-Petit's law, 3R, but low temperature it deviates significantly. That was, among many other things, signature of quantum mechanics. Einstein did one more signature of quantum mechanics. What is that? Photoelectric effect. It started, of course, with Planck's, right, black body radiation. Black body radiation also these vibrations are involved, because that is electromagnetic wave. Okay. Now you do this specific heat. Specific heat is this quantity just we did before. So, here we have to take the derivative of this quantity. Now, it is getting little complicated, they are not as simple as translation, but we would be able to take that like ds dt, again this guy comes below, then I take the derivative, and that becomes then e to the power minus h nu by kBt, and then and outside comes minus h nu by kBt square, minus another minus comes here. As I said, you minus 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 it becomes, and the minus 4 minus it becomes positive, and then you take derivative of this thing. There is fairly complex, you have to take derivative of this, that being minus 1 over t square, and then you have to take derivative of this guy, then again that same game minus and minus plus h nu by kBt square, and then you have this quantity which you also have to take the derivative, that then it becomes a square here because the denominator, then you take the derivative of that. When you do all these things, you get that square comes here, and so this is finally combining everything, this beautiful expression comes in. So this is a specific heat of a bunch of harmonic oscillators, which is so important in solids, because solids, remember, normal modes. Now what are the normal modes in solids? What are the normal modes in solids? How do we get normal modes in solids? Right. Yeah. Absolutely. That is called dynamical matrix. You are like that x1 minus x2 square plus x2 minus x3 square. So x1 minus x2, x2 minus x3, x4, x3, they are all coupled, but x1 and x2 are the positions. Instead, if I make the transformation, that is x1 minus x2 is the coordinate, so it is called displacement coordinate. Then you can decouple, and it is formally done by introducing what is called dynamical matrix and transformation. Then it becomes a bunch of harmonic oscillators, and the eigenvalues are the harmonic frequencies and eigenvectors are the modes. So solid state, much of solid state can be described as thermal properties, not the electronic properties. Thermal properties of solids can be described, and that is what Einstein and Debye did. So shown by Einstein, let us divide this expression specific heat of harmonic oscillators plays an important role in determining specific heat of solids. It continued to play a very important role, you know, and the guy who who got Nobel Prize for other things, Phil Anderson, has a famous theory of showing that at a very low temperature, this one shows an exponential dependence that does not work out. Debye corrected it by saying that Einstein assumed only one high. That is a beautiful work. He said whole solid has one frequency. That is Einstein did. Is this expression. Debye said no, that is not possible, because there is a distribution and also there is upper limit. When he introduced that fact, he got the T cube law. So specific heat of solids so it goes like that. This is 3R, Dulong-Petit's law. Here you find some signature of exponential, but here it goes as T cube. That is the one that Debye corrected by improving on Einstein's assumption of single mode. However, from now look at that, you take the case that I go to high temperature in this region here, this is the one I am going to look at now, okay, and that is by when temperature is large, then CV, you can look at that, take the large temperature, then it goes to 1. You expand this one because this is h nu by kBt small, okay. I expand that, I call it, we already called it x once before, we can call it x once more. So then e to the power minus x, I expand 1 minus x minus x and plus x square. So the 1 cancels 1, I keep the lowest order term which is x, there is a square here, it becomes x square, and that then cancels this because h nu by kBt, and then Cv is 3 nkb, okay. So which is nothing but 3R. So high temperature, this beautifully goes over to Dulong-Petit's law. This is an amazingly very pretty, very pretty part of statistical mechanics, that as I told you in the morning, that we get ideal gas law, we get the PV equal to RT, we get Cv equal to 3 by 2 R. So all these things we get the Sackur-Tetrode equation, but now we are seeing that it's a huge thing in we are explaining the properties of the specific heat of solids, which is enormously important and experimentally observable.